Our hypothesis was that if the ball is dropped in a more viscous solution, then it will experience more resistive forces, in this case a greater viscous force, which would be shown by the ball bearing's terminal velocity. We found that our data supported our hypothesis. In both the dish soap and the corn syrup solutions we used, the ball reached terminal velocity. In the dish soap, the ball had an average terminal velocity of 44.95 micrometers per second versus an average terminal velocity of 6.01 micrometers per second in corn syrup. From these values, we were then able to determine the average viscosity of each solution. The average viscosity of the dish soap was determined to be 1.446 times 10 to the negative second, and the average viscosity of the corn syrup was found to be 1.123 times 10 to the negative first. Thus, we conclude that if the ball is dropped into a more viscous solution, it will experience more resistive forces, resulting in a slower terminal velocity.
By graphing position, velocity, and acceleration, we were able to notice general trends and calculate terminal velocity for the ball bearings in both dish soap and corn syrup. The calculations were performed in a similar fashion for all trials, so we will just discuss one trial per type of liquid. When looking at the position versus time graph for dish soap trial 3, we can see that the slope is linear, which indicates that the velocity during this trial was constant. The average velocity for this trial was calculated by choosing 2 points on the line of best fit for the graph and averaging their velocities. Since the velocity is constant, the acceleration becomes 0 micrometers per second squared, as indicated by the acceleration versus time graph. Now we can look at corn syrup trial 2 and perform a similar analysis. The position versus time graph shows a linear slope, which is indicative of a constant velocity. We calculated the average velocity the same way we did in the trial for the dish soap. Due to this constant velocity, the acceleration becomes 0 micrometers per second squared, as shown by the acceleration versus time graph.
In order to complete this lab, we use Newton's second law, which states that the net force equals mass times acceleration. Because acceleration is the derivative of velocity, if velocity is constant, acceleration will be 0. This means that if velocity is constant, then the net force will also be 0, as F net equals ma. Because the ball bearings reach terminal velocity in this lab, which is a constant value, the acceleration of the balls is equal to 0, as is the net force acting on the ball bearings. To complete this lab, we also use the equation for viscous forces. Force viscous equals negative 6 pi times the viscosity constant of the liquid times radius times velocity. At terminal velocity, the viscous force is equal to the gravitational force, which was important to our calculations and shown and addressed later in this lab.
The results from this experiment allowed us to understand and observe a few physics concepts. The ball bearings were able to reach a constant in terminal velocity. This means that the acceleration was 0, since acceleration is the slope of velocity, and the slope of a horizontal line is 0. And because there is no acceleration, net force is equal to 0 as well. This is because net force equals mass times acceleration, and any number multiplied by 0 equals 0. We also found that the force of viscosity is equal to the force of gravity at terminal velocity, and that the force of viscosity is proportional to velocity. These concepts aid in performing the calculations for this experiment.
Our F net equation would be F net equals force gravity plus force viscosity. In order to find the viscosity constant, equation must equal force viscosity. By doing that, the equation would now be F viscosity equals F net minus F gravity. We know that at terminal velocity, F net will equal 0 because there is no acceleration. Now the equation is force viscosity equals negative force gravity. We know that the equation for force viscosity is negative 6 pi times viscosity constant times the radius of the ball times terminal velocity. We also know that the equation for force gravity is mass times acceleration due to gravity. If we sub in those two equations for force viscosity and force gravity, our final equation is now negative 6 pi times viscosity constant times the radius of the ball times terminal velocity equals mass times acceleration due to gravity. To find the viscosity constant for dish soap trials 1 through 3, the equation shown on the previous slide was used and all the known variables were plugged in. The only variable that remained was the viscosity constant. The number that was the result of the equation is the viscosity constant as shown at the end of each of the trials calculations, and it is unitless because the viscosity constant is a unitless number. The graphs shown are histograms and are used to visually show the average terminal velocity and average viscosity constant for dish soap. The average terminal velocity of the ball and dish soap was found to be 44.95 micrometers per second. This can be seen by looking at the average velocity graph on the left. The curve is a standard distribution curve and used to show what the average terminal velocity is. By looking at the peak of the curve, the average terminal velocity can be determined. The average viscosity of dish soap was found to be 1.44 times 10 to the negative 2. The idea for this graph is the same as the graph on the left. The peak of the standard distribution curve is the average viscosity for dish soap based on the viscosities of dish soap found on the previous slide. To find the viscosity constant for corn syrup trials 1 through 3, the equation shown earlier was used and all the known variables were plugged in until the only variable that remained was the viscosity constant. The number that was the result of the equation is the viscosity constant and is shown at the end of each of the trials calculations. The idea for these graphs is the same as the dish slope's average terminal velocity in viscosity constant graphs. The average terminal velocity of the ball in corn syrup is 6.01 micrometers per second, which is much slower than the terminal velocity for dish slope. The average viscosity for corn syrup is 1.123 times 10 to the negative first. The viscosity constant for corn syrup is much higher than the viscosity constant of dish soap.